All right, guys, so this video is on Hess's Law. All right, so we're going to be working with Hess's Law here. And I wanted to just separate all the different types of calculating delta H. So if you remember from class and whatnot, when we calculate delta H, that stands for enthalpy. And the units that enthalpy is measured in is kilojoules per mole reaction. Now, depending on what type of information you have given, there's several different ways to calculate delta H. This one is known as Hess's Law. So first, let's talk about what information will be given to you. What you will see in your problem is information about different compounds, and there will be delta H of formation. All right, so what you see right there is delta H with a little sub F, and it has a little not symbol right there. Anytime you are given this type of information, you're always going to do Hess's Law. What delta H of formation means is it's how much energy it takes to make 1 mole of that particular compound. So for ammonia, for an example, it takes negative 46 kilojoules for every mole to make 1 mole of ammonia. Now, when we say to make 1 mole of ammonia, what we're making this from is from its single elements. So we'd be reacting nitrogen plus hydrogen to form ammonia. And it takes that much energy, and it's actually releasing energy because it's negative, in order to make 1 mole of that. So you have different compounds here. You have different delta H of formations. Since this is information for just 1 mole of a compound, if I had like 2 moles of NH3 in a balanced reaction, I have to pay attention to my coefficients, because if there's 2 moles of NH3, then that means I need to take 2 times negative 46 to figure out how much energy I have for there. Another thing you have to pay attention to is when using Hess's Law, elements are 0. The reason why is because it doesn't take any energy to make elements, they're just naturally occurring. When we find these delta H of formations, you see the little not symbol right there. We learned that in electrochemistry. That means that we have standard conditions, which is 25 degrees Celsius, 1 atm, and 1 molar. So now let's talk about what Hess's Law, how do we find that value? This is the equation here. Delta H of the reaction, so that's the enthalpy for the entire reaction, is equal to the sum of the delta H of formations of my products minus the sum of my delta H of formation of my reactants. So this is the equation we use here. Remember, if we have elements in my products or reactants, those are 0. If we have more than 1 mole of my reactants or products, we have to multiply that number by that to figure out that value. So pay attention to the fact that this is products minus reactants. Later on, we're going to talk about an equation that's actually opposite of this. This equation is on your equation sheet, so you don't have to memorize it. You just have to know where to locate it on your equation sheet. So the technical name for this is Hess's Law. You'll see in the note packet that it is known as the Big Mama equation. And the reason why is because I can use this equation for delta H, I can use this equation for delta S, I can also use this equation for delta G, and we'll learn that a little bit later on. If you are in the notes with me, the NIMSY notes, we are on page 6. What I'm going to do is go through a couple of examples, just so you can get the hang of using this equation and show you how to use that. So let's scroll down to, or I'll scroll, you turn. Let me get my mouse here to page 7, and we have a couple of, oops, sorry. Let me get back in here. All right, here we go. So now I'm on page 7, and it says, given the information above, calculate delta H of the reaction. So I look at the information that's given to me, and I see that I have delta H of formations. So right here, delta H of formation. So that tells me I'm going to have to use Hess's Law, which is delta H of the reaction is equal to the sum That's supposed to be a summation, and that looks horrible. Sorry about that. Delta H of my products minus the summation of delta H of my reactants. So now all I have to do is plug in all of this information. One thing that I personally like to do, I like to go through here so I don't get confused to see if I have any free elements. If I have any free elements, then I know that those are automatically 0. So I'm going to take the sum of all of these energies for my products and subtract it from the sum of my energies of my reactants. So starting with delta H of the reaction, I'm just going to plug in those energies. Remember, if I have more than 1 mole, then I have to multiply that number. So I'm going to put this all in big brackets. We'll start with aluminum oxide. There's 1 of those, so it's 1 times negative 1676. It's the summation, so that means I'm going to add all these together. 1 times aluminum chloride, which is negative 704. Plus 3 times NO, so NO is here, 3 times 90, plus 6 times water in the gas form. So water in the gas form is given here, so it's 6 times negative 242. All right. So that is all of my products. Now I'm going to subtract all of my reactants. Aluminum is 0, so 3 times 0 is just 0. Ammonium perchlorate is NH4ClO4, and it's 3 times that, so it's 3 times negative 295. Now it's just a matter of plugging all of this stuff in your calculator. So make sure you do the correct order of operations. I have to take all of this value first, and then I have to subtract that value. And what you should get for your answer right there is negative 2,677 kilojoules per mole reaction. Don't forget to plug in your units, or put your units at the very end, because they will not give you credit for a correct answer unless you have the correct units involved. So negative 2,677 kilojoules per mole reaction. And because I have a negative quantity there, that means that this reaction overall is exothermic. So I'm going to take some time to do one more. This is exercise 9 that is on the bottom of page 7 in your notes. Notice here how I want to calculate the delta H of formation for glucose. So I'm given the overall delta H of the reaction. And for this particular problem, it's written in the reaction. Remember, whenever you have your energy written in the reaction and it's in the product side, that means that the reaction is exothermic. And since it's exothermic, this is actually going to be a negative 2,800 kilojoules per mole reaction quantity. If I would have had my energy written in the reactant side, then that would have indicated that my reaction was endothermic, and it would be a positive delta H quantity. But since this is on the product side, it's a negative delta H quantity. So I have to make sure that I plug that value in correctly, whether it's positive or negative, or it could change my whole answer. So delta H of the reaction is equal to the sum of my products minus my reactants. So I go through here and I say, do I have any free elements? And I see that oxygen here is a free element. Even though it's diatomic, it's a free element. And so therefore that value is 0. So I'm going to plug in my products 6 times CO2. So 6 times CO2, which is negative 393.5. Plus 6 times water in the liquid state, so that's 6 times negative 285.8. And those are my products, minus my reactants. So my reactants, I don't know glucose's delta H of formation. That's what I'm trying to solve for. So I'm just going to call that X. Now, what do I set all of this equal to? I have to set it all equal to the delta H of the reaction. Oops. Okay, sorry, I erased it. I had to rewrite it. So I have to set this equal to delta H of the reaction. So that, again, is given to me right here. And since it's a product, it's negative 2,800 kilojoules per mole reaction. So now it's just a matter of plugging this in correctly, being able to solve using the correct order of operations. Now, what you'll actually see, if I take all of this value and I subtract it to this side, or add, depending if it's negative or positive, which that would probably be a negative quantity. So I would add it to this side, you get positive 1276 is equal to negative X. We don't want the negative delta H of formation of glucose. We just want the positive quantity. So I'm going to distribute the negative 1 through here. So that means that the delta H of formation for glucose, C6H12O6, is equal to negative 1276 kilojoules per mole. And that is my final answer there. So I hope this helps you with delta H of formation, knowing what to plug it in for that. So when I'm working with delta H of formation, I'm going to use Hess's law, which is the sum of my products minus the sum of my reactants. You could have to solve for the overall delta H of the reaction. You could also have to solve for the delta H of formation of one of those.